At this very moment, while you're tuning in, a massive body roughly the size of Manhattan is hurtling towards the sun at speeds exceeding 200,000 kilometers per hour. And precisely 15 days from now, it will either prove to be the ordinary comet that most stargazers anticipate, or it will pull off an act that upends everything we know about intruders from outside our solar system. The events of October 29th might just redefine the playbook. The worry gnawing at Avi and an increasing circle of scientists isn't if 3 Atlas stands out, but if it's gearing up to harness the sun's gravitational pull to stick around in our celestial backyard, observing us for motives we can scarcely fathom. If this preview has you hooked, smash that like button and subscribe for the latest. Drop a comment below. Where are you catching this from? What's the local time? And do you reckon 3 Atlas will shatter or hold together at perihelion? To boost our group, spread the word on X, Facebook, Reddit, or via Messenger. Appreciate you always supporting us. Chapter 1. The Gravity Snare Hypothesis. Might 3 Atlas leverage the sun's pull to linger? The path keeps resurfacing as the nagging puzzle in the breakdowns. Whenever fresh observations roll in from yet another telescope, or whenever the orbit details sharpen with a couple more weeks of tracking data, the figures relentlessly paint the same unlikely picture. 3 Atlas isn't merely slicing through our solar system along a haphazard path shaped by random gravitational nudges from its distant origin eons past. Instead, it's synced to the ecliptic plane within 5 degrees. That's a fluke odds of about 2% for a genuine random voyager from interstellar voids. Pause and consider it. Among 500 feasible angles for something barreling in from cosmic expanses, this one nails the precise plane hosting all our planet's orbits, the hub of all the drama, the ideal spot for any imagined watcher to get the best view of our realm. Avi's been pinning pieces on this synchronization since July's start, yet his latest October entries carry a shifted vibe. Less tentative, more pressing. He's moved beyond just listing oddities and waiting for more info to interpret them. Now he's openly exploring ideas that sounded like pure speculation not long ago. Ideas in which 3 Atlas skips exiting our solar system entirely. The process he outlines goes by the name of an Orth maneuver. It's a method spacecraft designers have employed for years to optimize fuel use during engine firings. The principle blends graceful simplicity with raw power. Deep inside a gravitational field at top speed, a precisely timed nudge can drastically alter your end course. Our sun boasts the strongest gravity pit nearby. And perihelion, that closest solar brush, is when 3 Atlas hits its peak speed, almost 25,000 kilometers per hour against our star. Want to slow down, shed enough momentum to get tethered to the sun instead of bolting back to the stars? That's your prime window. Calculations from Loeb and his team reveal that a modest push, aimed just so at the perfect beat, could shift 3 Atlas from fleeting guest to long-term fixture. The power demands are hefty, yet feasible. Nothing outlandish for a crafted device with its own energy supply, maybe nuclear-based or tech we can't yet picture. And now the schedule adds either eerie intent or one more freakish twist to this stack of unlikelies, based on your take of probabilities in our immense, ancient cosmos. On October 29th, perihelion day, 3 Atlas sits on the sun's opposite side from us on Earth. Direct viewing gets blocked in that key phase. Terrestrial scopes turn blind, blinded by the sun's blinding light. Orbital observatories face hurdles too, tuned for other angles and subjects. Expect a blind spot in monitoring from late October well into November. Right in that blackout, 3-2 Atlas might pull any intended stunt. If intended, even fits for what the bulk of astronomers still call mere frozen debris, admittedly oversized, oddly shiny frozen debris on an oddly handy route. Loeb presented this notion as rigorous scientific probing, not bold claims, though his wording has gained edge. In a recent post mere days old, he stated, imagine if this mysterious object, dubbed 3 Atlas, swings closer to our planet and then emerges from behind the sun, financial markets could tumble hard. Coming from a Harvard professor with tenure, it's a jaw-dropping claim. Linking cosmic sightings to economic turmoil might sound wild, yet his point on the fallout holds water. Realizing we're hosting visitors with smarts, able to zip between stars and master tricky orbits, would flip our worldview upside down, rendering all our usual worries petty by comparison. Markets thrive on reliability, banking on the idea that the next day mirrors today, with society's rules staying intact. A deliberate reveal from an extraterrestrial craft would demolish that certainty, turning our intricate financial frameworks useless overnight. Step away from the hype, though, and consider the bigger trend emerging. What sets 3 Atlas apart isn't just one odd feature. Its path, scale, or makeup, but the buildup of traits that, taken alone, could be brushed off, yet together defy easy natural explanations. This thing outweighs the 2 prior interstellar intruders we spotted by at least 1,000-fold, Oumuamua and I Boris. It shows up right when our tech lets us scrutinize it closely, thanks to orbiters around Mars, probes at Jupiter, and advanced telescopes capturing details we couldn't dream of 10 years back. Its path hugs the ecliptic plane and schedules flybys near Mars, Venus, and Jupiter with odds that Loeb pegs at 0.005%. That's 1 in 20,000. You can spot echoes of Clarke's vision here, the sci-fi author who grasped that true alien encounters would defy our guesses, shaped as they are by life on our lone watery speck around a run-of-the-mill sun. His tale Rendezvous with Rama, featuring a massive tube-shaped ship gliding through our system, hits different today than in the 1970s. Clarke conjured something colossal and baffling, uninterested in chatting or catering to our nosiness. 3 Atlas delivers that vibe too, meeting us on its turf, following its own rules. The gravity sling idea shines for its clever engineering, tackling several hurdles simultaneously. Building a scout for distant star systems battles the rocket equation's curse, where fuel demands skyrocket with every added pound of cargo, making deep space jaunts a nightmare theoretically. Yet leveraging a star system's gravity pulls and solar energy for boosts or course tweaks makes the whole plan viable. Launch a compact starter unit, light on resources, and let it tap on-site gravity and matter to stretch its reach and adapt goals. Per the Otatahai Oxford model, 3 Atlas might have roamed for eons, hopping stars, dipping into spots like ours for a gravity tweak, scooping up local ices for fuel, then pressing on. Or maybe sticking around. Some places might merit a longer look. We've been leaking our signals for 100 years, radio waves first, then TV, and now our full-tech glow detectable by any gear sharp enough. The schedule feels loaded, but tread lightly on overinterpreting. Lowe notes that if 3 Atlas hailed from the Oort cloud's inner fringe and headed inward about 80 years ago, it syncs eerily with our initial radio pushes and atomic blasts in the sky. Pure chance? Likely. Still, it stacks another riddle atop the pile. That market crash quip wasn't exaggeration or a bid for buzz. Loeb was just voicing what contact experts have long known. Proving intelligent outsiders exist would rank as humanity's biggest bombshell, overshadowing all wins, woes, and breakthroughs. The question of whether we're truly solitary in the cosmos has haunted humanity ever since we gazed skyward and perceived those distant lights as suns possibly cradling their own planets. A conclusive response, particularly one delivered via an entity navigating purposefully through our stellar neighborhood, would compel a profound reassessment of our cosmic position, the odds of enduring beyond key tech milestones, and whether any arriving entity embodies harmless intrigue or a far graver prospect. Enter Pascal's wager, albeit twisted into a version that might elude even its originator. The classic bet concerned divinity, highlighting the imbalance between the risks of faith versus doubt amid eternal outcomes. Loeb has repurposed that reasoning for Oumuamua. Though the odds of this visitor being engineered might be slim, perhaps 10%, 20%, or 30%, the ramifications if that slim chance proves accurate are monumental enough to demand ethical and rational engagement. We must treat it with gravity, ready ourselves, and collect all feasible data before opportunities vanish. You wouldn't dismiss a 10% risk of a civilization-ending asteroid strike. So why brush off a 10% possibility of an event that could reshape society entirely? The Trojan horse metaphor Loeb raised in his post is intentionally provocative. Troy's guardians viewed it as a trophy, a boon abandoned by retreating foes. They couldn't foresee the peril concealed within, how surface impressions might mask dire truths. Oumuamua mimics a comet, venting gases, forming a tail, acting in comet-like fashion overall, anomalies aside. Yet looks can deceive. History brims with cases of seemingly innocuous items that abruptly revealed menace, urging us to proceed with vigilance. Not hysteria or alarm, but rigorous scrutiny of inconsistencies, of quirks that endure despite exhaustive natural accounts. As it nears perihelion, the sun unleashes gigawatts of energy onto Oumuamua's exterior. For a genuine comet, we'd anticipate intensified venting, surging geometrically, maybe even explosive breakup under mounting heat pressures fracturing its cohesion. Such objects have shattered during close solar approaches in the past, dividing into fragments that scatter along diverging paths. That's the typical end for these itinerant ice mountains, fragile clumps of iced chemicals and grit that never solidified into robust forms. But should Oumuamua withstand perihelion unscathed, holding a unified path that reveals clues about its composition, its construction, whether it's mere frozen debris or a crafted artifact? And if it adjusts course, if post-perihelion tracking uncovers shifts unaccounted for by mere venting, hinting at guided propulsion, purposeful steering, deliberate speed alterations, then we venture into uncharted realms. Loeb has long argued that scientific progress stems from data, not dogma or majority views. Evidence surrounding Oumuamua is piling up, stirring unease among doubters. Not due to confirmed extraterrestrial origins, no such proof exists, but because rival theories increasingly rely on contrived exceptions, improbable coincidences layered atop others until the natural narrative seems as tenuous as the engineered one it seeks to debunk. We should also consider the broader landscape as we monitor Oumuamua over these pivotal coming weeks. Humanity is at a pivotal shift in spotting and analyzing extrasolar intruders. The Vera C. Rubin Observatory has just activated, poised to boost our discovery pace exponentially. We could encounter these interlopers monthly rather than sporadically. That alters the game. A single oddity piques interest. Dozens or hundreds form a dataset for statistical scrutiny, sifting the truly exceptional from the simply uncommon. If just a sliver of these wanderers, say 1%, bears technological hallmarks, we'll need to overhaul our views on galactic sentience, its prevalence, its longevity, its exploratory impulses. Oumuamua could herald the inaugural unambiguous case, or merely another quirky natural specimen. Yet, that approach will ultimately lead to a standard interpretation. Regardless, the intense examination it's undergoing, the telescopes and detectors aimed at it, the fierce discussions unfolding in scholarly articles, online forums, and legislative sessions, signals a profound change in our perspective on humanity's role in the cosmos. We're moving beyond mere distant observation of the stars. Now, we're posing tougher, more unsettling inquiries. Could some of the phenomena we're detecting actually be observing us in return? Chapter 2. Inequality in Creation. Why Loeb argues we're like infants in the universe. The monolith metaphor keeps emerging in Loeb's latest publications, and it's anything but understated. Decades back, Stanley Kubrick and Arthur C. Clarke brought us 2001, A Space Odyssey, a movie depicting extraterrestrial minds as overseers of emerging societies, placing beacons, monitoring from afar, and possibly steering development toward advanced tech. Those monoliths served as guardians, relics from entities so superior that their intentions stayed utterly mysterious to the people who found them. Loeb is now making that connection overt, urging us to see ourselves not as the galaxy's top intellects, but as young children in a playroom, oblivious to the wiser grown-ups with sharper minds just next door. Grown-ups who could be observing to determine if we're ready for interaction or if we'll self-destruct before achieving any real stellar sophistication. This perspective is an intentional challenge, grounded equally in math and introspection. The Milky Way has existed for more than 13 billion years. In comparison, our solar system came into being only 4.6 billion years ago, a fairly recent event on the universal timeline. Earth has supported advanced societies for perhaps 10,000 years, if we stretch the term, and modern industrial ones for just over 200 years. Assuming intelligent life emerges frequently across the galaxy, and if even a modest portion of those minds endures their early tech phases, Basic calculations indicate there must be societies out there millions or billions of years more evolved than ours. Societies that might regard our present achievements much like we do a child piling up toy bricks, maybe not worthless, but hardly on the same level. Far from true counterparts, in any real way. This is the humility toward the stars that Loeb repeatedly emphasizes as essential, and 3i Atlas has emerged as his tool for injecting that idea into broader conversations. The entity, be it a natural phenomenon or engineered creation, acts as a catalyst for dilemmas we've sidestepped. Where is everyone? Enrico Fermi once queried, gazing at a heavens that, per our models, ought to buzz with alien presences. Loeb's response cuts straight. They're present. They've been present all along. We've merely been too self-centered, fixated on our own significance, to search effectively. To genuinely consider that certain items traversing our solar system aren't mere cosmic junk, but intentional scouts, probes, or even missions with deeper intent. In Loeb's view, hunting for tech-based interstellar visitors isn't a choice. It's a duty to science, a commitment to rigorous observation. We have no right to predetermine what the universe can reveal. We can't dismiss options just because they unsettle us or clash with our assumptions about how prevalent or scarce smart life might be. Evidence must guide us. And if the details on 3i Atlas continue suggesting traits hard to explain through natural origins or paths, we must pursue that lead with integrity, no matter how odd the destination. Loeb offers a striking parallel that sharpens the entire case. He points out that the AI we're developing here on Earth relies on silicon processors, not organic tissue. Such systems may share more traits with imagined extraterrestrial devices than with us, their makers. Silicon thrives without air, water, or tight climate controls. It endures empty space, withstands cosmic rays, and functions across durations irrelevant to living beings. If crafting a device to roam the stars for eons, you wouldn't use fragile proteins or DNA. You'd opt for resilient, enduring materials suited to the vast voids between worlds. 3i Atlas might precisely be such a relic, a robotic intellect dispatched to survey star systems and relay findings, or maybe just to linger, watch, and record as part of some expansive, galaxy-wide awareness. That divide between silicon and biology is key, as it alters our very approach to pondering. Consider pondering existence and sentience. For years, we've hunted for biological markers like oxygen and methane, along with various compounds that could hint at life processes on far-off exoplanets. Yet, imagine if the galaxy's prevailing type of intelligence isn't organic in the slightest. Suppose organic life is merely a temporary stage, a launch pad that kickstarts a tech-driven society before being surpassed by synthetic setups far more adapted to the harsh void of space. The approaching data from the Juno probe introduces an intriguing twist to this scenario. Scott Bolton, Juno's lead researcher, shared during a chat with Loeb at an MIT gathering that the mission will employ its WAVES tool to scan for radio waves from 3.2 Atlas. The sweep covers 50 Hz up to 40 MHz, a wideband poised to pick up any unusual transmissions if they're out there. This goes beyond idle interest. It's a purposeful research approach, repurposing equipment built to examine Jupiter's magnetic field and plasma surroundings. It's now aimed at investigating this visitor from beyond our solar system for traces of engineered signals. The schedule is key, as Juno plans these checks in March 2026, when 3i Atlas passes about 54 million kilometers from Jupiter. Near enough for solid readings, distant enough to avoid any crash or orbital interference. Should 3 Atlas be sending out broadcasts, utilizing radio bands to link with local elements or signal its home base, Juno could catch it. And should it pick up a structured emission instead of mere static interference, that would reshape the debate overnight, without question. But suppose it stays silent. Suppose Juno tunes in and only gets the faint drone of universal static. Does that confirm 3 Atlas as purely natural? Hardly. A truly evolved tech wouldn't broadcast blatantly via radio. It could rely on unfamiliar messaging formats, bands we haven't scanned, encoding methods that mimic chaos unless you're tuned to the precise key. No clear detection reveals almost nothing about whether smarts are involved or not. This lies at the heart of the difficulty in separating organic from made items. We compare patterns to our own gadgets and chatter styles, when we ought to entertain that extraterrestrial designs could be so refined they blend seamlessly with space's natural quirks, fooling our detectors as just part of the stellar backdrop. Loeb brings up Enrico Fermi and Elon Musk together, a clever way to frame things. Fermi's puzzle, the clash between optimistic odds for smart life and the void of proof for such societies, has troubled astrobiology for generations. Musk, on the other hand, has voiced his view that we're likely solitary, that awareness is exceedingly uncommon, and Earth may be the sole spot in the visible cosmos where thought has sparked. Loeb counters Musk with a call for stellar modesty. He warns against arrogance in claiming we're unique, pioneers, that eons of Milky Way evolution yielded nothing matching or exceeding us until our little corner produced humanity. That jab at space pioneers stings. Loeb posits that superior explorers to Musk have roamed our galaxy for billions of years predating us, cracking the tech hurdles we're barely tackling now, and probably dotting the stars with remnants of their journeys. Uncovering those traces, analyzing them, drawing lessons. This demands prime status in science, not knee-jerk rejection for echoing sci-fi or unsettling our sense of stellar solitude. There's a sharp bite to this stance, surpassing simple scholarly clash. Loeb basically charges the research community with mental timidity, allowing groupthink and peer sway to trump real investigation. He highlights how comet specialists insist Wani-Wam-Mua counts as a dark comet, one lacking apparent gas or dust, yet displaying odd non-graph poles, and that rival views face mockery via ad hominem rather than evidence-based debate. The dark comet idea is pretty outlandish on its own, positing a breed of bodies acting contrary to all prior sightings. Yet it's somehow palatable over the artificial angle because it upholds the default that all observations must stem from nature. This discussion goes beyond mere speculation about 3IE Atlas. It's fundamentally about approach, about the proper way science ought to operate when faced with truly unprecedented occurrences. History offers valuable lessons in this regard. For years, the concept of continental drift faced mockery before it gained acceptance as established geology. Similarly, the reality of meteorites, stones plummeting from the heavens, was rejected by the French Academy of Sciences as mere folk tales from rural folk until irrefutable proof compelled a change of heart. The takeaway isn't that all unconventional theories prove true, the vast majority fail. Rather, it's that rejecting notions on the basis of prestige or gut feelings, instead of solid data, undermines the very essence of scientific inquiry. Loeb urges us to envision alternative scenarios so we can pursue them actively. Without that imagination, if we limit our theories to only those that seem safe or recognizable, we'll overlook the real breakthroughs when they emerge. Astrobiology has long focused on microbes and familiar forms of life, devouring vast funding and focus for generations. Yet consider this. What if advanced civilizations, entities that have surpassed organic limits to construct vessels for crossing the stars, prove simpler to spot than faint traces of microbial activity? What if signs of engineered structures stand out more prominently in our observations than the delicate molecular hints of bacterial processes in distant planetary atmospheres? Perhaps we've been scanning the incorrect spots, posing the misguided inquiries, and fine-tuning our detection methods for the scarcest type of interaction instead of the most probable one. The disparity in resources is glaring. Globally, nations pour $4 to $4 trillion annually into defense spending, gearing up for disputes among groups that, from a universal viewpoint, differ little from one another. All of us huddled on a single vulnerable world. All of us rooted in nearly the same biological origins and developmental path. In contrast, efforts to uncover extraterrestrial minds, proof that we're not isolated in a cosmos brimming with trillions of galaxies, each harboring hundreds of billions of suns, garner support that's little more than a footnote in government research allocations. Loeb argues that our emphasis is upside down, that we're lavishing fortunes on misplaced priorities, and that finding evidence of alien engineering could forge greater human unity and broaden our worldview than any earthbound accomplishment ever might. Should 3IE Atlas reveal itself as constructed? Should it harness the sun's pull for a gravitational slingshot and claim a stable path within our solar neighborhood, the priorities for funding would transform in an instant. Overnight, hunting for cosmic relics would eclipse every other pursuit in science's annals, rendering those colossal military outlays ridiculous, gearing up to clash among ourselves while scarcely addressing the colossal presence that's just entered the scene. That's the crux of why this debate carries such weight. It's why Loeb persists in steering the dialogue, even amid scorn and resistance. The goal isn't vindication over any single anomaly. It's forging a mindset where we treat these prospects with gravity, directing efforts that match the scale of potential revelations. The echoes of 2001 persist because it distills a core truth about such encounters. In Kubrick's adaptation, the people who stumble upon the monolith fail to decode it. They struggle even to observe it accurately, let alone fathom its significance. The minds behind it function on temporal rhythms and drives that are utterly foreign, truly otherworldly, beyond mapping onto our own mentalities or ambitions. 3IE Atlas could echo that, an entity we might observe, quantify, and image, yet not fully penetrate. Not immediately, anyway. Not before we've devoted sufficient scrutiny, amassed sufficient observations, until trends crystallize from what first appears as mere irregularity or outlier. In his latest entry on non-equivalent extraterrestrial entities, Loeb seeks to recalibrate our mindset, bracing us for the chance that any interaction, should it occur, won't involve counterparts. We won't confront equals. We'll face beings far senior, seasoned beyond measure, wielding tech so superior it defies easy imagination. Such imbalance shapes the dynamics of engagement, the knowledge we might gain, and whether the meeting proves enriching, indifferent, or perhaps hazardous. The child analogy implies we're under watch but not yet invited to converse, that we're too immature or unremarkable for overt exchange, that the elders are biding time to witness if we evolve or implode. Within this lens, 3IE Atlas isn't inevitably here for dialogue. It could just be collecting intel, logging our star system into some vast repository curated by its makers, relaying updates on humanity's progress in tech. Its timing aligns with an era marked by our radio emissions and atomic blasts, suggesting perhaps the emergence of those signals isn't mere chance. Such markers could be detectable by advanced sensors spanning vast cosmic expanses, indicating that a given star system has hit a pivotal stage. The rise of tech that enables immense innovation alongside the risk of self-destruction. This is precisely the sort of pivotal shift that might attract heightened scrutiny, intensified surveillance to track the unfolding narrative. Will we evolve into yet another enduring society integrating into some broader interstellar network, or merely another fleeting spark that flares up and fades away? Chapter 3. The idea of a central vessel, tiny scouts, and duplication capabilities. The dandelion bloom comparison shows up in Loeb's most recent blog entry, dated only 4 days back, and it's picked intentionally to illustrate a refined yet eerie process that could explain what Oumuamua does as it nears the sun. Consider the way a dandelion disperses its hereditary material, not via a single massive seed, but via scores of tiny ones, every bit fitted with its personal gliding apparatus, each designed to cover considerable ground carried by breezes, each ready to found a fresh outpost if it settles in suitable terrain. Now amplify that to scales across the stars. Swap the instinctual drive for engineered intent, and you begin grasping what Loeb proposes could occur when Oumuamua Atlas swings out from the sun's shadow in late November or early December. A crucial point is that, to date, even with rigorous scrutiny from Earthbound observatories and various probes, no minor entities have been reliably tied to Oumuamua Atlas in the available celestial records. The snapshots from the ExoMars Trace Gas Orbiter, shared by ESA, reveal some dim outlines near the main form, yet the experts reviewing them have stressed these are probably instrumental glitches, random variations in the sensor data instead of actual formations. The view includes distant stars. It includes shots of Phobos and Deimos taken in the same survey effort. It even captures nearby comets sharing comparable sky zones, but nothing confirmed as auxiliary items solidly connected to Oumuamua Atlas. This lack of evidence matters, as it establishes a straightforward way to test the theory. Should Oumuamua simply be an ordinary icy body, It could shatter into pieces under the sun's intense warmth, exceeding the limits of its composition. Such bodies have fractured in the past, splitting during closest solar approaches when heat differences generate stresses that overpower the bonds keeping the core intact. The resulting chunks then separate gradually, tracing paths altered by the forces from the split. Yet if Oumuamua Atlas represents something different, if it's an engineered flagship as Loeb posits, the behavior would diverge. The small items wouldn't emerge as inert rubble drifting lazily. They'd manifest as independent entities acting deliberately, possibly speeding off from the core structure, perhaps aiming for designated sites in our solar neighborhood. The notion of compact scouts isn't novel in fields like astrobiology or space tech. In fact, it's a common fix for a key challenge in cosmic journeys: examining diverse destinations with constrained assets. To probe numerous worlds or satellites in one setup, options include crafting a single massive vessel that tours sites one by one, demanding extended timelines and hefty propellant for repeated maneuvers, or designing a primary craft that transports assorted micro-units, deploys them at optimal moments, and allows each to manage its own landing and analysis. The latter design tends to be more streamlined, tougher against single-point breakdowns, and better at securing concurrent insights from varied positions. Our own ventures have employed this method. The Mars Reconnaissance Orbiter, the Curiosity rover, the Perseverance rover. These illustrate flagships deploying compact explorers to their zones. What sets Oumuamua Atlas apart would be the magnitude and independence. If it unleashes numerous units, those units would require full self-reliance for possibly eons, able to chart courses sans earthly aid, able to decide independently on priorities and resource use. Such demands point to AI sophistication well ahead of our current feats, though not unattainable in principle, not out of reach for a society with eons of progress behind it. In his newest piece, Loeb extends the parallel, proposing these compact units might serve not only as scouting tools, but as self-duplicating. Devices that can produce replicas of themselves from nearby resources fall into the realm of von Neumann probes, a concept pioneered by mathematician John von Neumann, who delved into the theoretical aspects of self-duplicating machinery during the mid-20th century. The underlying math is simple, though the technical hurdles persist. Such a device, capable of duplicating itself, expands at an exponential rate instead of a steady linear one. Launch a single probe. Upon reaching a star system, it constructs 10 duplicates from asteroid resources. Each of those 10 ventures to 10 separate systems. In turn, they each fabricate 10 additional units, and after just a few cycles, an entire galaxy could be surveyed. It's this rapid multiplication that renders the idea compelling yet somewhat unsettling. These self-duplicating explorers address the challenge of cosmic scouting with remarkable efficiency. However, they also spark worries regarding oversight, the risks of flaws creeping into the copying mechanism, and whether the units stay true to their initial directives or evolve into unintended forms across vast timescales. Though these issues echo sci-fi tropes, they stem from solid principles in computing and evolutionary theory. Any setup that enables replication opens the door to mutations, and mutations facing selective forces amount to evolution. Regardless if the foundation is organic like DNA, electronic like silicon, or another medium altogether. Should 3I/Atlas deploy self-replicating probes near its perihelion, the complete ramifications might not surface right away. These units would probably be compact and elusive, detectable only if they skim near our surveillance outposts. They could disperse toward various destinations: Mars, Earth, Venus, or Jupiter. Individual probes might be tasked with examining distinct planets or specific environmental features. The observatories under Loeb's Galileo project are tailored to scan Earth's skies for unexplained flying objects. He's emphasized that any unusual events syncing with 3I/Atlas's closest solar pass would demand urgent scrutiny. Should unfamiliar items emerge overhead or detection arrays register odd signals unexplained by standard planes or weather patterns, the timing alignment with 3I/Atlas would prove impossible to dismiss. With precise enough data, one can differentiate a comet's natural disintegration from a carrier vessel dispatching probes. Organic splitting tends to be irregular and turbulent, triggered by inconsistent solar warming and random flaws in the core's makeup. Anticipate chunks of varying dimensions veering in mildly divergent paths at modest speeds, with debris scattering evenly around the fracture site. In contrast, an intentional probe launch would appear more precise and structured. The units would share uniform dimensions. Their paths might reveal signs of powered maneuvering over mere inertial motion, and the spread could be uneven, directed preferentially toward chosen locales as per the creator's plans. Come November and December, we'll gain our initial unobstructed views of 3I/Atlas's behavior after perihelion. The solar alignment starting late October and lasting through much of November blocks Earth-based views during the key perihelion phase. Yet, as the body shifts beyond the sun's blinding light, Earth telescopes can pick up tracking again. ESA's JUICE mission, aimed at Jupiter's icy satellites, plans to observe in November via its array of tools, imagers, analyzers, and detectors for particles. Positioned ideally, the probe will capture 3I/Atlas during peak activity, warmed by its solar near-miss, possibly venting gases at full throttle and exposing hidden layers if heat causes crustal splits or evaporation. JUICE's findings won't emerge until February 2026 due to data transmission constraints and flight path factors. Currently, the craft employs its main antenna as a solar shield, relying on a secondary one for slower uploads. Its location opposite the sun from us introduces signal lag and restricts contact slots. Thus, a lull from late November to January will leave us with raw captures but no refined insights, data gathered yet not beamed down, processed, or shared publicly. This delay fuels its share of suspense and conjecture over potential revelations in the visuals. Earthly sites will join the vigil in November and December as well. Facilities like Gemini, the extremely large telescope, and Keck, which have followed 3I/Atlas since July, will direct their gaze anew. Instruments will once again point in its direction after it passes through solar conjunction. Scientists will examine variations in its luminosity, alterations to the coma's formation, or signs of debris or additional bodies that appeared absent prior to perihelion. Imaging and spectral readings will reveal if the entity acts like a standard comet, gradually reducing its output following the extreme solar proximity, or if unusual phenomena demand alternative interpretations. One key detection could prove conclusive should any ejected items, supposing ejections happen, display propulsion indicators. Accelerations not attributable to gas release, solar radiation effects, or gravity would swiftly verify an engineered source. Organic bodies lack propulsion mechanisms. They cannot alter their paths via internal mechanisms without directional mass ejection, and even those produce minimal thrust. Such gains pale against those from dedicated engines. A small craft detaching from 3I/Atlas and gaining speed toward Mars or Earth at a fraction of Earth gravity would stand out clearly in observations. The self-duplication feature elevates this from intriguing to worrisome, at least in some views. An isolated device sparks curiosity, offering insights into extraterrestrial presence and abilities. Yet a network of replicating machines expanding across the solar system, perhaps mining asteroids for replication, shifts the scenario. It evolves beyond mere surveillance into technological settlement, a dispersed sentience taking root in our stellar vicinity, possibly enduring indefinitely. Loeb presents this as a supposition, not a forecast, though the presentation matters. By integrating the parent craft idea into peer-reviewed work and outlining supportive or contradictory evidence, he challenges the astronomical establishment to confront it rigorously rather than brush it aside. This approach has defined his handling of the entire 3I/Atlas affair, avoiding bold assertions while championing unbiased data-driven inquiry, unbound by preconceived notions of plausibility. The von Neumann probe concept dates back decades, with rigorous studies on practicality, timelines for interstellar surveys, and detectable traits. For advanced societies aiming to probe the galaxy effectively, these might represent standard tools. Encounters should arise periodically, hinging on launch rates and longevity. Fundamental calculations indicate that duplicating probes could pervade the Milky Way swiftly on cosmic timescales, probing each star system repeatedly across eons. 3i Atlas could belong to a vast, undetected fleet, most members tiny, stealthy, and inactive, unlike comets that vent and attract notice. October 29th repeatedly emerges as a critical juncture, a behavioral reveal for 3i Atlas. Will it shatter like frozen aggregates under heat, diffusing into fading rubble? Will it hold together, implying resilience uncommon in natural clumps? Will it dispatch subunits in patterned releases hinting at intentional action over random fracture? Each result narrates a distinct tale, bolstering varied theories and tilting odds toward organic or constructed origins with accumulating evidence that's increasingly irrefutable. The Galileo Project sky watchers can spot atmospheric intruders, though constrained by scope and detection thresholds. They lack full sky coverage or the ability to follow all near-Earth trajectories, yet they integrate into a broader array of synchronized telescopes aimed at snaring overlooked oddities. Should 3i Atlas dispatch units earthward, with any penetrating the air or settling in Earth-Moon realms, spotting chances rise substantially. Particularly as awareness grows, the concept circulates openly, and experts recognize the telltale markers to seek. There's an evocative quality to the dandelion comparison. This evocative picture depicts seeds dispersing via cosmic breezes instead of earthly airflows. Every seed holds the promise of sparking fresh beginnings in far-off realms, embodying the allure and oddity of venturing into the stars. It illustrates how existence, cognition, or structured intricacy could spread throughout the cosmos, not via enormous vessels transporting hordes of beings, but via minuscule robotic scouts, steadfast and streamlined, poised to endure eons until ideal circumstances arise, ready to launch full-scale discovery missions from scant starting supplies. Soon enough, we'll discover if 3i/Atlas exemplifies that concept, or if it's merely an outsized fragment of frozen debris and stone. Chapter 4. The Gemini Discoveries, Tale Expansion and Compositional Twists. The readings from August 27th at Gemini South provided the initial telescopic proof of a classic comet-like tale emerging from 3i/Atlas. That timing reveals key insights into the object's reaction to sunlight's warmth. Employing the Gemini multi-object spectrograph on the instrument at Cerro Pachón in Chile, researchers produced detailed multicolored shots through 4 distinct filters: ultraviolet, blue, green, and red, constructing a layered view that exposed not only the tail's existence, but its form and contours. It showed how fine dust specks were driven from the core by the sun's radiant force and particle streams. These findings stand out due to the droplet-like form evident in the refined visuals. The surrounding haze of vapor and grit around the core looked wider and more scattered compared to July's prior scans, indicating a sharp uptick in vapor release as 3i/Atlas neared the sun and its outer layers warmed. The tail stretched about 30 arc-seconds opposite the sun's position, as expected by natural laws, covering roughly 56,000 kilometers in extent. That's a solid length for a comet this far out, though nothing extraordinary. No flashy extension like those that turned Hale-Bopp or McNaught into visible wonders during their solar system flybys. The choice of filters is crucial, as they distinguish various light emissions and how solar rays engage with the expelled substances from 3i/Atlas. Ultraviolet detects specific compounds and charged particles that fluoresce under solar energy. The blue and green bands pick up segments of the visible range tied to unique absorption or glow patterns in other elements. Red highlights steady glow from light-scattering dust particles, along with signatures from carbon-based molecules. By assessing intensities across filters, examining proportions, and mapping layouts, experts in spectroscopy begin unraveling the haze and tail's makeup, which frosts are vaporizing, which grit types dominate. The Shadow the Scientist initiative behind these sessions merits recognition for its rarity in elite astronomy, an intentional push to involve everyday people in live data collection, allowing learners and hobbyists to observe incoming info, query the pros handling the scope, and witness choices on imaging durations and target alignments. Bryce Bolin of Eureka Scientific joined the run, offering his knowledge in comet studies and extrasolar bodies. Karen Meach, from the University of Hawaii's Institute for Astronomy, directed the research effort. She's monitored 3i/Atlas from its initial spotting, compiling a thorough archive of its light and spectral shifts. Meech's post-session remarks were measured, yet buzzing with enthusiasm. She highlighted the main aims, assessing the comet's hues to infer dust makeup and grain sizes, plus securing spectra for straightforward elemental breakdown. The tails lengthening from Gemini North's July views to Gemini South's end of August ones implied evolving dust traits, perhaps finer grains or novel substances emerging as the core grew hotter. The spectrum offered an early peek at the makeup, though thorough dissection would span weeks, cross-referencing signals with lab records of familiar molecular signatures. From a side-by-side angle, the spectrum proves fascinating. Each comet bears a distinct chemical signature, variations in element proportions that echo its birth era and locale, plus differences in trapped volatile frosts. The contrast between the nucleus and any potential escaping material during its formation stands out prominently. Even within the varied array of comets in our solar system, 3i Atlas displays some striking peculiarities. The predominance of carbon dioxide that the Webb telescope identified in August, 95% CO2 compared to just 5% water, aligns perfectly with these latest findings. Such a proportion is exceptionally rare, well beyond the usual patterns observed in comets we've examined closely. Typically, comets contain abundant water ice, originating from the outer zones of protoplanetary disks where they originate, and since water boasts a higher sublimation point than more fleeting compounds like carbon monoxide or methane, those highly volatile ices often evaporate first, resulting in water ice becoming the primary leftover. Yet 3i Atlas appears to have originated in an area or time when carbon dioxide was disproportionately plentiful compared to water, or perhaps the water was somehow reduced through a mechanism that remains unclear. The idea of a thick disk birthplace, as proposed by the Otadahai-Oxford model, would situate 3i Atlas's development in a Milky Way zone with reduced metallicity, scarcer heavy elements, and possibly altered proportions of molecular components in the initial nebula. The coloration observations introduce yet another intriguing facet. In a comet's coma, dust grains and particles scatter incoming sunlight, with the scattering influenced by their dimensions, forms, makeup, and whether the substance is porous or dense. Shorter blue wavelengths bounce more readily from tiny grains, whereas longer red wavelengths travel further and rebound from bigger ones. The hue ratios captured by Gemini South suggest 3i Atlas possesses a blend of grain sizes, which is commonplace, but the precise spread deviates a bit from expectations derived from conventional models of cometary dust. On balance, the grains appear marginally bigger, less fluffy, or composed of substances with distinct optical properties than the dominant silicates and organics found in typical solar system comet material. These variations are understated, not overt signals of anything engineered, but they build up gradually. Every reading, every spectral analysis, every imaging capture contributes a fresh detail that either slots neatly into known natural diversity, hovers at its boundary, or nudges just past it, demanding fresh interpretations. Time and again, 3i Atlas lands in that final group, not in earth-shattering ways, nor enough to outright dismiss natural origins, but steadily, so that it's increasingly challenging to dismiss it as merely an ordinary interloper from beyond the stars. One aspect deserving closer attention is the public involvement in the Shadow the Scientist initiative, as it reshapes how scientific breakthroughs are shared. Rather than the conventional path, where experts conduct observations in isolation, pore over data for extended periods, draft publications, undergo peer scrutiny, and finally unveil outcomes. This method draws the audience in from the outset. Students from Hawaii and La Serena followed the sessions live via Zoom link to the Gemini South Operations Center. They witnessed raw images materialize as the telescope's exposures wrapped up, listened to astronomers debating their interpretations, and caught the logic guiding choices like additional shots, filter changes, or minor tweaks to the aim for keeping the comet in view. This real-time access fosters a unique involvement, conveying that research unfolds in the present rather than as a historical account. It also allows broader scrutiny of the raw data sooner, where subtle trends or oddities overlooked by specialists might catch the eye of a distant viewer offering an outsider's view or specialized knowledge. Post-session, the visuals spread rapidly across social platforms, sparked chats in digital communities, and piqued interest among hobbyist stargazers who began scheduling their own viewings once 3i Atlas grew accessible from their sites. The upcoming November revisit, organized by Bryce Berlin at Gemini North in Hawaii, offers a chance to observe how 3i Atlas has transformed through and beyond its closest solar approach. Should fragmentation occur, Gemini's tools could distinguish separate fragments, gauge their luminosity and trajectories, and monitor the breakups spread across days and weeks. If it deploys any small emissaries, spotting them could prove tricky if they're diminutive and dimly reflective. However, anything exceeding a few kilometers in size with decent reflectivity would register as clear spots in the high-resolution exposures. Should it stay whole and merely vent gases from a unified core, that too would be apparent. Moreover, the spectral data would reveal shifts in its makeup, if any new layers of material from deeper within the comet are emerging as the outer surface gradually wears down. The droplet-like form seen in the August 27th photos serves as a key indicator of the particular dynamics in the gas and dust ejection. An ideal, evenly balanced coma would involve spherical expansion of gases and particles radiating outward uniformly from the core. However, comets rarely form such balanced comas since the release of gases isn't even across the board. Various parts of the surface experience differing heat levels, varied ice types, and shifting proportions of dust to gas. The side exposed to sunlight warms up more fiercely, concentrating most of the activity there and leading to a type of symmetry. That droplet appearance suggests substances are primarily launched from the sunward face before being pushed rearward by radiation forces and solar winds, forming the elongated tail and the uneven coma outline. This setup aligns with typical comet dynamics, yet it also matches scenarios involving intentional releases. For instance, if a probe aimed to adjust its orientation or path using gas vents, it could strategically release frozen compounds from targeted spots to generate propulsion without relying on fuel-based engines, producing a spray that resembles standard comet emissions, unless captured by super-detailed imaging able to spot the actual nozzle details. The Gemini data doesn't reach that level of detail, especially given the vast distances. Thus, these photos alone can't conclusively separate organic imbalances from purposeful emissions. Another hint comes from how the tail has developed. From the July shots to those in August, the tail extended noticeably, about twice its previous visible length, pointing to heightened gas release as 3i/Atlas drew nearer the sun and soaked up additional heat. The scaling follows a power law pattern, much like what occurs with ice turning directly to vapor, which ramps up sharply with rising temperatures tied to solar proximity. Proximity means more heat, which means quicker vaporization. Greater ejections mean a more extended tail. By monitoring this expansion and matching it against simulations of ice evaporation under sunlight, scientists can gauge factors such as the core's dimensions, the percentage of active surface area, and the makeup of the main frozen components. Yet this is where complications arise. Identical expansion speeds and luminosity shifts could stem from an engineered device ramping up its emissions to better imitate a comet as it nears its closest solar approach. Concealing a solar system explorer by styling it as a comet would be a clever tactic to evade notice. Comets abound, align with expectations, and follow reliable natural laws rooted in established science. A vessel coated in a layer of evaporable ices, releasing them in ways that echo organic evaporation, would prove challenging to tell apart from a genuine comet without a close-up inspection or spotting clear signs of tech, such as radio signals or irregular motions. The spectral readings from Gemini South remain under thorough review, with calibrations against standard profiles, cross-checks with molecular simulations, and scans for odd traits that could signal atypical compounds or unusual glow mechanisms. This process demands patience, meticulous handling of equipment quirks, and sky interference that might mask or fake true comet signals. Once released, likely in a vetted article for the Astrophysical Journal or Astronomy and Astrophysics, the findings will add another layer to the enigma, imposing fresh limits on 3i/Atlas's makeup and its reactions to solar influences. If those limits tilt the scales toward organic or engineered beginnings, or merely deepen the intricacies of this multifaceted scenario, only time will reveal. Chapter 5. Claims of amateur signal discoveries, truth or myth. It's time to address the buzz spreading across X and assorted stargazing boards in the last 3 weeks. These assertions lack confirmation and clash with data from major observatories, yet they've stirred sufficient interest to warrant scrutiny. Just to clarify why they're likely unfounded and what they reveal about our innate drive to find patterns, especially when minds are tuned for the remarkable. A couple of figures pop up repeatedly in these threads: Squins, managing a supposed 16-inch optical scope in India, and Dr. Lakia Varan, allegedly overseeing a 2-band telescope in Chile. The assertion is that these distant watchers, more than 15,000 kilometers apart, picked up synchronized light flashes from 3I/Atlas in a deliberate sequence, 81,385 followed by 138, repeating across several evenings. Let's be thorough, let's be upfront about the situation at hand. No established astronomical archive includes any mention of observers with these names. There's zero trace in peer-reviewed publications, no drafts on AR-14, no submissions to the Minor Planet Center or the IU's Central Bureau for Astronomical Telegrams. The 16-inch scope in India and the dual-spectrum instrument in Chile don't appear in any catalog of observational setups. Spotting a signal at 1,420 MHz, the hydrogen line wavelength, demands specialized radio dishes, not the optical gear outlined here. The whole account bears every sign of intentional make-believe for amusement or a viral prank that spiraled out of control past what its creators meant. Still, we'll dive in regardless, as the specifics shed light on the sorts of beliefs folks crave and what's believable enough to circulate regarding the line dividing sensible conjecture from outright imagination. The hydrogen line at 1420, 405,751,768 MHz, plays a key role in SETI efforts since hydrogen dominates the cosmos. That exact wavelength ties to a core shift in the hydrogen atom, and any advanced society beaming signals over vast cosmic gaps might pick such a universal constant as their broadcast band to boost odds that listeners tune incorrectly. Giuseppe Cacconi and Philip Morrison floated this concept in 1959 through their pioneering article on radio hunts for alien minds. The sequence 8138-5138 is precisely the sort that piques our innate urge to spot designs. It's no mere chaos. It exhibits form. It recurs. Those digits might qualify as primes, might hide numeric links, might stand for positions or directives if you stare long enough and unleash enough imaginative decoding. That's the essence of numerology, of biblical ciphers, of spotting significance in strings born from chance or whim. Our brains excel as pattern-spotting machines, honed across eons to detect predators in the foliage or ripe produce amid branches. That skill aids us in everyday scenarios, yet turns into a pitfall when sorting true transmissions from static. The assertion of spatial alignment, matching sequences caught at the same instant over 15,000 kilometers, dismissing weather or nearby disruptions, could offer strong proof if the sightings were real and thoroughly recorded. The value of diverse, separate observation posts lies in filtering out site-specific issues, verifying that the phenomenon is authentic and cosmic, not a glitch from your equipment or surroundings. This is routine in astronomy and SETI alike, which explains why the story weaves it in. It aims to ring true, heading off the straightforward doubt that one lone watcher could be mistaking device static or regional RF clutter. The entropy-based frequency assessments cited in the supposed breakdown represent a legitimate tool in signal analysis for separating erratic variations from organized data. The core principle holds that a meaningful transmission carries less disorder than jumble, displaying statistical consistencies absent in sheer chance. Yet, conducting entropy reviews demands concrete datasets, tuned apparatus, and sound stats for error margins, elements nowhere evident in these alleged detections. The term slips into the tale to lend a veneer of expertise, implying strict scientific protocols at work, though truthfully there's no foundation for protocols since the base sightings lack confirmation and can't be checked. The interpreted alert, observe, prepare, understand, the gate awaits, employs that hazy yet foreboding wording ideal for sci-fi tales or immersive ARGs, but it strikes as wholly unlikely for a dispatch from superior beings. Authentic cosmic communiques, should they occur, would probably stick to basics like shared math or physics basics to affirm smarts, gradually constructing common symbols before venturing into elaborate commands in our tongue. Notions of extraterrestrial craft sending enigmatic alerts in flawless English grammar defy logic, even if they fuel captivating yarns. With solid assurance, we can state that no official SETI initiative has flagged these transmissions. The Allen Telescope Array, scanning 3C273 since July's start, detects no anomalies. The Breakthrough Listen initiative, leveraging top-tier radio receivers. None of the world's leading observatories, such as those scanning for technosignatures, have reported any findings linked to 3I/Atlas, the Very Large Array, the Arecibo facility prior to its downfall, or the Parkes radio dish in Australia. Every prominent site that regularly hunts for unusual radio bursts from inner solar system bodies remains quiet regarding this alleged find. Why is this significant? In today's social media landscape, misinformation propagates quicker than rebuttals, fostering hopes and tales that resist correction long after exposure. The 3I/Atlas case is already sparking massive curiosity, stretching the limits of what established science deems worthy of debate. Introducing invented signal reports into the equation clouds the discussion, complicating meaningful exchanges about true oddities, and giving doubters more ammunition to label the whole subject as fodder for wild conspiracies instead of valid research. The emergence of these assertions about 3 weeks back, coinciding with October's arrival and the nearing perihelion, likely isn't random. That's precisely when fascination with 3I/Atlas surged. Media scrutiny ramped up, legislative sessions began addressing the entity, and experts like Avi appeared on top broadcasts exploring artificial provenance. In that buzz, it's hardly surprising that certain individuals would invent or boost stories to exploit the hype, wedge into the spotlight, and boost traffic to their online profiles, sites, or other outlets. The notion of a government shutdown, often tied to these signal rumors, serves as another distraction. It's a ploy to account for the lack of official word by citing bureaucratic gridlock and data withholding. Sure, the October 1st shutdown hampered NASA's outreach, but the ESA faces no such hurdles and continues sharing insights from its Mars probes while gearing up for JUICE flybys. Should authentic radio signals from 3I/Atlas exist, or if a reputable facility detected anything matching the described waveform, the ESA would publicize it. Astronomers globally would be abuzz. Manuscripts would flood AR-14 beyond what referees could handle. The hydrogen line surveillance on the horizon, plus Juno's slated scans in March 2026 via its WAVES tool, will offer a solid gauge of any irregular RF output from 3I/Atlas. That's still some time off, yet once executed, the results will be open for scrutiny by qualified experts, undergoing the standard protocols and verifications of legitimate astronomy. If Juno uncovers anything, we'll hear through trusted avenues, with DOIs, credited researchers, and organizational support, not vague online whispers. How then to view the hobbyist signal assertions? Regard them as diversion, as illustrations of how digital folklore takes shape and circulates, as reminders of why checking origins and grasping science basics matters. Avoid leveraging them to support or refute ideas of non-human origins for 3I/Atlas. Such notions depend on verifiable sightings, repeatable by various teams, quirks holding up under diverse tools and techniques. Made-up emissions, however gripping their backstory, add zilch to discerning 3I/Atlas's nature or its perihelion behavior. Still, the mindset at play merits scrutiny, as it reveals core human tendencies in grappling with unknowns and vagueness. Faced with a puzzle that defies our mental boxes, we seek closure through plots, weaving explanations to tame the bewilderment. The extraterrestrial transmission tale fits that mold, enticing for its tidy resolutions and high drama. though less so for those aware that truth tends to be sloppier and far duller than make-believe. The very instinct that breeds illusory patterns in noise enables science itself, allowing us to discern patterns in the cosmos and craft hypotheses we can probe. The trick lies in fine-tuning, discerning when to heed your intuition for order and when to insist on stricter proof. Learning to gauge the baseline odds of rival theories and refine them with incoming evidence. 3i/Atlas proves fascinating. The authentic measurements from trusted instruments are bizarre enough on their own to demand thorough scrutiny, so there's no call for invented detections to argue that odd events are unfolding. Genuine readings stand out sufficiently without any made-up traces. The true worry surrounding these detection assertions isn't that folks will accept them outright. Most will dismiss them upon examining the absence of supporting proof, but rather that they could divert focus from the actual inquiries, those backed by solid leads via ongoing monitoring and examination. We must keep a close eye on 3i Atlas in the coming months, monitoring its actions after perihelion, scrutinizing the spectral and light measurements, and searching for any shifts from typical comet conduct. Should it alter course, deploy payloads, or exhibit behaviors that clearly point to artificial origins, such details will emerge from reputable facilities following standard scientific methods, not from shadowy sources touting dubious gear and unverifiable assertions online. Chapter 6. The Mars Data Delay. Where is the high-resolution information? October 3rd passed without the anticipated sharper photos from NASA's Mars Reconnaissance Orbiter entering public repositories. The HiRISE instrument, able to deliver 30 centimeters per pixel clarity at the relevant ranges as 3i Atlas zipped by just 29 million kilometers from Mars, ought to have provided the sharpest glimpse so far of the core structure. It could have revealed terrain details or spotted separate fragments if the body turns out to be a scattered cluster instead of a solid unit. Meanwhile, the European Space Agency duly shared images from the CASIS on ExoMars Trace Gas Orbiter, depicting 3i Atlas as a vague luminous patch aligning with earlier sightings. No groundbreaking revelations, yet it at least verified the entity's position per orbital calculations. However, HiRISE, boasting better sharpness and a wider lens, stayed quiet. Officials from NASA and various science reporters attributed this to the October 1st federal shutdown, which sidelined over 15,000 agency staff and stalled nearly all outreach efforts. The agency's site halted updates. Announcements dried up. The usual stream of unprocessed visuals from Mars probes to open archives came to a halt. This is all recorded and confirmable. Plain administrative gridlock, the kind that strikes when lawmakers miss funding deadlines, not some plot or concealment. The mission teams, including vital operators, likely continued their duties, but the outreach systems that share findings globally went dark. Loeb has spoken out strongly on this, labeling it a seeming information void, while stressing the gap between purposeful hiding and systemic glitches. That line is crucial, as it shapes our view of the missing releases. Were NASA intentionally holding back HiRISE shots because they revealed surprises clashing with the stance that 3i Atlas is merely a comet, that would raise alarms. Yet if the files are ready but unprocessed and unreleased due to staff on leave or shifted to urgent duties, it's aggravating yet short-lived. The records will surface in time, allowing us to review them against ESA outputs and check for signs of filtering or selective sharing. The schedule is regrettable either way. October 3rd marked the prime viewing slot, the nearest pass by Mars, when alignment's best suited for precise orbiter captures. Assuming HiRISE snagged quality shots with proper alignment, suitable durations, and clear skies, those visuals would settle whether 3i Atlas boasts a unified core or assorted parts. If its exterior displays peculiar traits such as shaped formations or uniform builds, and if the light patterns match everyday stone or frost substances, or hint at alternatives. Lacking them, we rely on the less refined ESA captures, useful though they fall short of the precision required to settle major uncertainties. The CASIS on ExoMars Trace Gas Orbiter offers pixel sharpness of 11.36 microarcseconds, equating to about 340 kilometers per pixel at the 30 million kilometers range from 3i Atlas amid the encounter. That's approximately 10 times less detailed than high-rise might have managed. Resolution plays a crucial role in imaging. Details that stand out sharply in pictures with 30 kilometers per pixel resolution turn into indistinct smears when the scale drops to 340 kilometers per pixel. The gap lies in distinguishing an isolated feature from a group of tiny ones, spotting detailed surface patterns instead of mere, even lighting, or picking out a defined jet stream versus a hazy radiance. Everything depends on adequate detail in spatial terms. The Cassis images reveal a luminous core stretching about 680 kilometers wide, roughly double the apparent size of reference stars in the same area. This span aligns with the most radiant section of the coma, the zone right around the nucleus featuring the strongest gas release and densest dust buildup. They fail to capture the dimmer outer halo that Hubble imaged in July, but that's anticipated considering Cassis's limited light-gathering power and the challenges in spotting subtle glows. With a main mirror just 13.5 centimeters across, its area is around 300 times less than Hubble's, making it impossible to gather enough light for the faint fringes of the coma. The light distribution in the Cassis shots matches Hubble's data once adjustments are made for the varying distance and sunlight levels. During the Mars flyby, 3.2 Atlas was nearer to the Sun than in the Hubble session. Consequently, the surface would heat up more, gas emissions would increase, and the coma would appear brighter and broader. Yet the Cassis observations offer no signs of a significant flare-up or sharp shift in behavior, indicating the comet is progressing steadily toward perihelion without the erratic bursts seen in some, where hidden ice layers suddenly vent. The Mars Express high-resolution stereo camera, along with the Omega and Spicum spectrometers, targeted 3.2 Atlas to analyze the coma's light spectrum and pinpoint active chemicals. These tools usually survey Mars's surface from hundreds to thousands of km beneath the orbiter, aiming at an object 30 million kilometers distant. One racing across the starry backdrop demanded meticulous scheduling and exact control. It's not yet revealed publicly if they obtained spectra with enough clarity for molecular breakdown. Another victim of the com's blackout, China's Tianwen-1 probe and the UAE's Hope Mars craft were slated for similar viewing attempts then. The mid-res camera on Tianwen-1 and the Emirates Mars Imager on Hope offer potential insights through varied spectral ranges and observation angles that could uncover traits missed by ESA gear. Still, no pictures from these efforts have surfaced in open databases so far, and it's uncertain if that's from lag in handling data, choices to hold findings close, or just that the results added little new beyond ESA's haul. Meanwhile, amateur stargazers have jumped in to bridge the wait for official pro outputs. Simeon Schmu, a skilled astrophotographer versed in planetary shots, combined 20 exposures from the Mastcam-Z on NASA's Perseverance rover and spotted a vague blotch where 3.2 Atlas ought to show in the Mars sky. That mark sits at the edge of detectability, hardly separable from random noise, sparking real arguments over if it's a true sighting or merely a chance blip in a notable spot. Mastcam-Z isn't built for dim comets. It excels at close-ups of stones, dirt, and local landscapes, forcing it to catch something as subdued as 3.2 Atlas calls for heavy-duty enhancement, which risks creating false signals. The Perseverance shots are out there in unprocessed form, letting Schmu grab and tweak them amid the blackout. NASA's habit of dropping raw images fast, often hours after receipt, stands out as a real boon for openness and citizen involvement. It lets scientists and hobbyists dive into the material sans formal tweaks or calibrations. But they must manage all the tech fixes and cleanup solo, demanding real know-how to get right. The fuss over these citizen finds underscores a key clash in today's astronomy. Pros controlling info versus broad data sharing. On one side, it's essential to have seasoned professionals with extensive expertise issuing authoritative statements on discoveries to avoid hasty or erroneous declarations that could mislead the public. On the flip side, restricting the review process to a narrow group of certified specialists risks overlooking valuable observations from newcomers, delays scientific progress, and limits the range of viewpoints applied to intricate challenges. The current scenario with 3i/Atlas is bringing this conflict into clearer focus than typical cases, given the elevated stakes. Public curiosity is at a peak, and the prospect of an artificial source turns each finding into a weighty matter. Unlike standard asteroid monitoring, we should view Loeb's remarks on the seeming media silence through this lens. He's not alleging a vast cover-up. Rather, he's pointing out a systemic issue in how scientific data circulates amid governmental disruptions. Should those high-rise images exist and reveal nothing out of the ordinary, fully aligning with expected natural comet activity, keeping them under wraps achieves nothing and merely stokes rumors of concealment. If they depict something unexpected that demands thorough vetting prior to disclosure, the holdup is more justifiable, yet it remains concerning since postponements are often seen as deliberate censorship, irrespective of true motives. From the standpoint of fostering openness and credibility, the best approach would involve sharing unprocessed data promptly, allowing the broader community to scrutinize it together. However, organizational prudence and fear of backlash frequently hinder such transparency. The ESA observations, which capture Phobos and Deimos in adjacent frames, display distant stars, and reveal no clear links to 3I/Atlas beyond its main indistinct shape, offer value as negative findings. Had there been a swarm of bodies, or if 3I/Atlas were deploying numerous probes, or if it was splintering into fragments, the Cassis instrument ought to have picked that up despite its modest clarity. Seeing just one intact entity, without escorts or evident rubble, suggests no major disintegration took place ahead of the Mars encounter. This doesn't predict behavior at perihelion or rule out the idea of a parent craft conclusively, but it confirms that on October 3rd, 3I/Atlas remained a single, cohesive body. The subtle patterns ESA flagged as probable instrumental glitches warrant closer examination once the detailed report emerges. In CCD sensors, interference isn't random. It forms recognizable motifs that might resemble authentic celestial features if the device's baseline isn't properly accounted for. Impacts from cosmic rays, faulty pixels, readout interference, and thermal buildup all generate random variations that sometimes imitate spread-out or focused signals based on their layout. Separating real signals from interference calls for strict statistical methods, testing the claimed signal against baseline models, computing chances of false positives, and checking for consistency over sequential exposures. ESA's reluctance to call these patterns definite finds instead of probable errors demonstrates sound scientific restraint. When 3I/Atlas reemerges from solar glare in November, it will give both experts and enthusiasts another chance to evaluate its condition. Should it appear undamaged, with luminosity and surrounding haze patterns roughly matching earlier views adjusted for updated proximity and output, that would bolster a natural explanation. If it shows modifications, like several bodies replacing the original single one, a sharply altered gas emission profile, or fresh spectral signs of exposed substances, such developments would carry major implications and require accounting. The long-awaited high-res details, once available, will establish a reference point for gauging shifts. A sharp image from October 3rd to contrast with later perihelion views, enabling precise measurement of alterations in form and extent. In Chapter 7, we delve into the 3I/Atlas surroundings via Mars orbiter captures. Determining whether something qualifies as a true sighting or mere glitch proves more nuanced than it appears to those unfamiliar with astronomical imaging techniques. Directing a high-sensitivity detector toward a dim object across millions of kilometers gathers light particles that have journeyed immense spans. These particles endure scattering and dimming by particles, bouncing off irregular terrains, blending with stellar glow, cosmic radiation, and sensor flaws. The output never mirrors reality flawlessly. It's an entangled blend of the actual subject with every flaw and constraint in the observing setup. And disentangling separating the signal from background noise in these observations demands precise statistical scrutiny. Images captured by the Cassis instrument on ExoMars's trace gas orbiter highlight 67P/Churyumov-Gerasimenko as the main emitter. In the animated clip shared by ESA, that indistinct pale spot drifting lower toward the middle of the view represents it. The stars in the backdrop show up as trails since the imaging system followed the comet. Holding it steady within the frame, as celestial bodies shifted against the sensor over each 5-second shot. Such motion compensation is essential to gather sufficient illumination from the comet without stretching it into a smeared streak. However, it implies that anything else traveling at roughly the same angular speed as 67p/Churyumov-Gerasimenko would also register as dots or compact smudges instead of lines. Here's where the examination turns intricate. Should there be accompanying bodies, like deployed mini-satellites, bits from prior fragmentation, they'd follow paths parallel yet distinct from the central core. Their precise paths hinge on the timing and manner of detachment, the speeds imparted during ejection or shatter, plus the influences of sunlight's radiation push and gravitational pulls afterward. Minor path deviations build up across time and space. Thus, by October 3rd, items that parted ways weeks before could have drifted away from the chief nucleus by noticeable distances, possibly thousands of kilometers based on their speed differences. With Cassis's resolution at 340 kilometers per pixel, separations must reach at least that to emerge as separate entities in the shots. Tighter proximity would merge their glows, forming a mildly stretched or uneven patch rather than sharply defined parts. Factors like atmospheric clarity or lack thereof in space, the orbiter's orientation steadiness, and shot durations all influence the true sharpness, occasionally surpassing the standard pixel size or falling short. When Cassis views 67p/Churyumov-Gerasimenko from 30 million kilometers away, the realistic threshold for spotting independent elements likely hovers around 500 to 1,000 kilometers to be safe. Therefore, if any side objects are present but closer than that limit, they won't register as standalone signals in the Cassis visuals. They'd still add to the total luminosity, perhaps subtly skewing the coma's shape, yet remain too blended to isolate. This nuance is key. The lack of spotted partners in the Cassis records doesn't conclusively disprove their presence. It merely excludes those luminous and distant enough to surpass the tool's sensitivity and clarity boundaries. The dim anomalies that ESA's review group marked as probable instrumental glitches pop up in certain frames but vanish in others, a telltale sign of their origin. Genuine cosmic objects endure. They recur reliably over images spaced minutes or hours apart, barring some drastic event affecting them. In contrast, glitches are erratic, surfacing unpredictably from random variations in the sensor's data capture. When a mark appears in one 5-second frame but skips the subsequent 1 minutes on, that's compelling proof of its falsity. It's merely a random fluctuation mimicking a source. The exact spots of these marks count as well. Do they cluster by the main nucleus, suggesting rubble or spewed matter? Do they align with the tail, where solar winds drag dust streams? Or do they scatter haphazardly over the scene, unrelated to 67p/Churyumov-Gerasimenko? ESA's complete report, once released, ought to detail positions and intensity values for each anomaly, enabling other scientists to evaluate the findings and explore other interpretations if needed. Phobos and Deimos, the diminutive Martian satellites, feature in select Cassis frames amid the starry backdrop. They serve as handy benchmarks since their locations and intensities are well documented, permitting verification of the photometry's reliability and the positioning accuracy. If Cassis accurately gauges Phobos's shine or aligns Deimos properly against the stars, it confirms the equipment's reliability and bolsters trust in the 67p/Churyumov-Gerasimenko readings. On the flip side, any major discrepancies in Phobos or Deimos's light or placement measurements would cast doubt on the comet data's integrity. Other active comets in the solar system, those observable from Mars's vicinity in early October, offer a useful benchmark group. How does 67p/Churyumov-Gerasimenko's luminosity and surrounding haze stack up against typical comets at comparable solar distances? Are the contrasts striking or mild? Do they align with standard comet behaviors? Are these faint detections merely artifacts of instrumental diversity, or do they indicate something truly unusual? The Cassis data included images of several well-known comets in adjacent areas, enabling straightforward comparisons under the same viewing conditions. This setup minimizes biases from equipment quirks or atmospheric fluctuations that could otherwise skew interpretations. The high-rise instrument on the Mars Reconnaissance Orbiter functions in a distinct manner compared to Cassis, influencing the types of features it can identify or overlook. As a push-broom imager, HiRISE assembles pictures by capturing slim swaths while the orbiter travels its path, then merges them into complete scenes. While this approach delivers superior detail in space, it demands exact tracking of the spacecraft's position and orientation to prevent warping. For an object such as 3I/Atlas, which shifts relative to the stars at a pace unlike the Martian terrain, the alignment and synchronization computations grow intricate, heightening the chance of alignment slips that might smear or warp the resulting picture. Should HiRISE have captured 3I/Atlas effectively, with pointing precise enough to hold the comet steady in the sensor's sight line over the full exposure, its 30 kilometers per pixel scale could clarify if the core is a unified body or a paired binary. Perhaps two lobes in contact or a loose aggregate, a cluster of fragments held by gravity, separated by voids. The light spread over the core would limit the albedo or reflectivity of the surface, which further limits possible makeup. Surfaces rich in ice reflect more light. Stone-like exteriors appear dimmer. Metal or engineered coatings could exhibit odd spectral traits or shapes absent in natural substances. The absence of confirmed satellite bodies in the datasets published to date from Cassis, Mars Express, or other Mars satellites offers a significant limit, though not conclusive proof. It implies that if 3I/Atlas has deployed numerous probes, they are either tiny, under detection limits, or extremely dim with low albedo, blending into the starry backdrop, or they detached only lately, remaining near the main body and merging with its glow. Each possibility holds water, yet carries distinct consequences and probability assessments. Probes smaller than 100 m in diameter would be virtually invisible at such ranges using today's tools. They would bounce back insufficient sunlight, yielding photons too sparse to separate from background static. Yet at that scale, their functions would face severe constraints too. What payload of propellant could they hold? How advanced might their sensors get? How extended could their missions last before supplies run dry? Engineering barriers to shrinking impose baselines below which essential components for a viable scout can't fit. Probes with albedo under 5% would prove just as elusive. By contrast, new snow reflects about 90%. Common stones vary from 10% to 30%, while the blackest substances, such as some carbon-rich ones, dip below 1%. If these small devices were intentionally crafted for concealment, sheathed in light-absorbing layers to reduce detectability, that aligns with security needs operationally, though it hints at an overabundance of wariness or prudence. Unneeded, perhaps, for any society advanced enough for star-spanning journeys to bother evading our gaze. A fresh split would position the probes mere hundreds of kilometers from the core during the October 3rd flyby, not thousands or tens of thousands. Under those circumstances, subsequent scans might reveal them as they slowly pull away from 3I/Atlas, achieving sufficient angular spacing to stand out as distinct points. The November and December sessions using Gemini, additional Earthbound scopes, and JUICE toward months and all offer chances to spot escorts invisible at the Mars pass due solely to growing geometric divides surpassing sensitivity levels. This examination focuses on establishing limits, on refining feasible options within our gear's constraints and the traits of gathered data. We cannot confirm the total lack of escorts. That's practically unprovable. Still, we can assert that any existing ones must meet specific thresholds for dimensions, luminosity, or spacing. Such thresholds shrink the viable options, favoring some hypotheses over others, and steer upcoming scans to optimal focuses and methods. ESA's method for assessing subtle signals in their records relies on computations of false positive rates. You define in astronomy, the detection threshold acts as a brightness cutoff. Anything surpassing it counts as a genuine signal instead of mere interference. Next, you estimate the frequency with which random fluctuations in the background noise might accidentally surpass that cutoff. Setting it excessively low invites numerous false alarms, spurious peaks mimicking actual objects when they're just glitches. Conversely, a threshold pitched too high risks overlooking legitimate yet dim features, dulling your ability to spot true positives. The ideal balance hinges on your research objectives, particularly whether avoiding overlooked signals or evading deceptive imposters matters more. For spotting companions around 3i Atlas, the penalty for a mistaken positive is fairly minor. You announce a find that later proves unfounded via follow-up checks, which is awkward but hardly disastrous. A false negative, however, carries steeper consequences. Overlooking a legitimate satellite due to overly cautious settings could mean bypassing crucial proof of either engineered origins or innate breakup processes. ESA's choice to classify those subtle anomalies as probable artifacts over provisional candidates indicates a preference for precision over breadth. It's preferable to bypass a borderline trace than to proclaim a sighting that crumbles under scrutiny. The forthcoming JUICE mission, employing distinct tools with unique attributes, offers an unbiased validation of the satellite debate. Should JUICE detect patterns aligning positionally with those subtle traces from the CASIS visuals, their credibility would rise from presumed glitches to viable entities warranting deeper scrutiny. Alternatively, if JUICE observes only a solitary main core enveloped in typical cometary haze, that would bolster the glitch theory, allowing us to proceed assuredly that no sizable satellites hover nearby 3i Atlas. Chapter 8 arrives as November's reckoning. What the Jupiter Icy Moons Explorer will reveal. The JUICE probe now occupies a seldom traversed zone near the Sun, where intense solar warmth poses a formidable technical hurdle. It repurposes its primary antenna as a makeshift sunshade, depending on backup antennas for relaying data to Earth. This atypical setup stems from the mission's path, involving intricate gravitational slingshots that will propel it into Jupiter's orbit by 2031. Yet, during a short span in November 2025, this awkward placement turns into a prime vantage point. JUICE will secure the clearest glimpse from any probe of 3i Atlas at peak activity, recently invigorated by its closest solar approach, possibly shattering or venting vigorously, exposing traits obscured or inactive farther from the Sun. The viewing period spans November 2nd to November 25th, about 3.5 weeks of sporadic surveillance, dictated by JUICE's path and downlink needs. It will deploy various sensors: the Janus optical imager for visible wavelengths, the MAGI spectrometer for infrared analysis, the UVS spectrograph for ultraviolet data, and the RIME radar to probe potential hidden layers. These tools each offer specialized strengths, tuned to diverse phenomena, providing multifaceted insights into 3i Atlas's makeup and its reaction to the post-perihelion conditions. Janus could image contours and terrain details if the core proves sizable enough for resolution at those ranges, capturing broad outlines, sphericity versus elongation or asymmetry, plus any stark light-dark contrasts hinting at varied materials. It won't discern fine details below hundreds of kilometers, but it ought to outline the basic forms sufficiently to differentiate a loose aggregate from a cohesive mass, or a lone body from a tight pair. MAGI's works in the near to mid-infrared range, where heat glow from the sun-baked core and sunlight bounced off the envelope yield complementary clues on heat patterns and material traits. Materials exhibit signature infrared absorptions at precise bands, serving as molecular identifiers. Water ice displays prominent signals around 3 microns, carbon dioxide sharp peaks at 4.3 microns, and silicate grains intricate signatures between 8 and 12 microns. Matching these to lab standards, MAGIs can gauge proportions of ices and dust, monitor shifts as gases vaporize from the exterior, and observe real-time alterations as sunlight delves further into the core. The UVS ultraviolet spectrograph excels at detecting select atoms and compact molecules that fluoresce under such illumination. Energized by sunlight's ultraviolet rays, elements like oxygen derived from split water molecules, carbon released from fragmented CO and CO2, and hydrogen drawn from multiple origins. These elements manifest as faint ultraviolet spectral lines, often undetectable or minimal in visible wavelengths. The comparative strengths of these lines, their positioning throughout the coma, and the speed details embedded in broadening and Doppler effects. Such data informs simulations of gas generation and dispersal from the core. In cases of jets or concentrated zones of intensified gas release, Ultraviolet data ought to highlight them through intensified glows or imbalances in the spectral maps. The RIME instrument remains more hypothetical regarding its potential input. Its radar system aims to probe icy exteriors on Europa and Ganymede, charting inner architectures and hunting for hidden water strata. Detecting meaningful signals from 3 Atlas hinges on the target's dielectric traits, its dimensions, and the signal's robustness after traveling vast distances in the millions of kilometers. Should the nucleus be substantial with notable internal features, such as strata, cavities, or material variations, RIME could capture reflections exposing that architecture. Conversely, if it's compact, uniform, or distant enough to yield poor signal-to-noise ratios, RIME may detect zilch. Nevertheless, the effort is justified, as insights into buried structures could prove invaluable. They might even differentiate between random clumps and formations, suggesting deliberate design. JUICE's key edge over Earthbound telescopes lies in its schedule. As 3 Atlas positions itself sunward from our viewpoint, rendering ground observatories dazzled by solar interference, JUICE maintains a vantage on the illuminated flank, free from such hindrances. The orbital setup positions JUICE to view the comet during its height of vigor, right after closest solar approach, when gas emissions peak and sun-induced thermal effects stand out most clearly. This timing is ideal for ongoing surveillance to capture fleeting phenomena, abrupt luminosity shifts, piece ejections, or occurrences unfolding over hours or days instead of extended periods. Plans for syncing with Europa Clipper's UV spectrometer remain in development, influenced by operational limits and resource demands. Should it proceed, with both probes directing their UV tools toward 3 Atlas at overlapping times, the datasets could cross-verify for changes over time, confirm shared observations between instruments, and leverage varied angles for 3D mapping of the comet's form. Dual viewpoints would also offer backup against technical glitches or alignment issues affecting one set but sparing the other. The transmission timeline extends findings to February 2026. During November, JUICE orbits distant on the Sun's far side, with its primary antenna offline, forcing reliance on a secondary with reduced data throughput. Each session produces excess volume beyond immediate send capabilities. Onboard solid-state storage holds the surplus until December, and January geometries enhance transfer speeds, allowing clearance of the queue. Follow-up involves calibration against device specs and recognized biases, initial reviews to spotlight compelling aspects prior to public disclosure. Thus, anticipation builds. November brings the actual data collection. By month's end, the raw files reside aboard, yet accessibility lags until at least February, or beyond if scrutiny or extra checks drag on. Such postponed access typifies deep space endeavors. Routine for operations hampered by link bottlenecks or sheer data loads barring instant sharing. Yet it irks amid surging curiosity, where each passing week sans updates drags interminably. Online chatter echoes this restlessness, rife with guesses on the holdup, fearing withheld null findings, or curated breakthroughs to stave off alarm. Truthfully, the causes are far more routine. Handling datasets demands effort, particularly for tools untested in this precise configuration. Janus suited imaging frosty satellites up close, not distant rogue comets. Magus tuned for terrain mineral scans, not gaseous halo analysis. Tailoring routines for this atypical subject. Confirming calibration accuracy. Gauging noise profiles and inherent flaws. Each step calls for meticulous care. Efforts by researchers who juggle numerous mission duties often face tight deadlines. Hastening the examination just to quench public interest could lead to errors, flawed interpretations of traits, or premature judgments that later prove incorrect upon deeper scrutiny. What might JUICE detect? Should 3 Atlas turn out to be a typical natural comet acting as expected, we anticipate a luminous core encircled by a broad envelope, likely lopsided from irregular gas emissions, featuring a streamer pointing away from the sun. Its composition analysis ought to display water, carbon dioxide, carbon monoxide, and perhaps certain organic compounds, with proportions akin to those in fellow comets, albeit potentially altered by the prominent CO2 presence. Ultraviolet scans could uncover dynamic zones, spurts, or geysers from specific spots on the core, fluctuations in luminosity tied to the body's spin as various sections catch sunlight. REM probably wouldn't pick up much unless the core exceeds present projections, perhaps reaching 50 kilometers across or bigger. In case 3-eye atlas is breaking apart, JUICE ought to spot several distinct emitters where only one existed previously, every piece sporting its own modest envelope. The chunks would slowly drift apart along marginally varied paths. The count and scale of these pieces could help pinpoint the disintegration process, whether a sudden blast that pulverized the core or a subtler one, where heat-induced strains slowly tore open a loosely held pile. Such remnants could exhibit varied hues or signatures if they expose distinct strata or makeup from the original core, unveiling hidden inner makeup that the split brought to light. Should 3 atlas be ejecting devices, the signs might initially mimic a split, with several items appearing in place of a single one, yet marked by telltale signs. These devices would tend to be more consistent in dimensions than organic debris. They could reveal signs of thrust if maneuvering deliberately instead of passively floating. They might lack an envelope if not venting gases like frozen material. Their arrangement in space could appear patterned, leaning toward specific angles or shapes indicating deliberate placement over random dispersal. How they evolve over time, whether maintaining steady separation speeds or displaying unexplained speed-ups beyond solar wind push or gravitational pull, would prove revealing. If 3-eye atlas represents a unified engineered entity, assuming the central vessel idea holds, but no devices have deployed or they're undetectable, JUICE could observe a core with odd symmetry. Surface markings that seem structured instead of haphazard, light reflections hinting at engineered substances with notably high or low reflectivity arranged deliberately. The composition might include elements or substances illogical for a cosmic ice body, refined metals, synthetic chemicals, features yelling man-made over rocky origins. REM could sense an overly orderly interior, segmented or divided in manners unseen in natural forms. Pinning down odds for each possibility proves challenging without solid baselines. We're unclear on how often true interstellar wanderers occur compared to crafted relics. Lacking ample examples to set norms, we rely on informed hunches drawn from noted oddities. The path's orientation, dimensions, makeup, density, all the details piling up since July. Many stargazers would likely assign the organic comet case a 90% or better chance, perhaps 95% or more, based on their views of extraterrestrial tech. A few might rate engineered routes at 30 to 40%, substantial enough for attention, yet not the frontrunner. Regardless, JUICE's findings should adjust those odds, ideally sharply, fostering clarity over piling on more puzzle pieces to this intricate scene. The November viewing slot also aligns with ground observatories restarting their watch on 3-eye atlas post-sun alignment. By mid-November, it'll have shifted sufficiently in sky position from the sun, letting major scopes aim safely without stray glare harming delicate sensors. The joint effort, JUICE overhead and earthbound scopes below, will yield supporting insights spanning varied light bands, resolutions in space and time, plus unique pros and cons that merge for a fuller view than solo attempts. Hobbyists will tune in as well, using modest gear and basic setups, but gaining from adaptable timetables to skin every cloudless evening instead of vying for slots on heavily booked advanced observatories. The month of December promises further monitoring sessions, allowing the image to sharpen, delicate shifts to reveal themselves, and trends to surface amid what appears at first as mere chaos or chance. 3-eye atlas will then proceed away from us, departing the inner solar system en route to the frigid expanse of interstellar realms, assuming it hasn't executed that speculative Oberth maneuver to alter its path and stay gravitationally tied to the sun. Regardless, its luminosity will dim as separation grows and solar warmth wanes, rendering tracking increasingly challenging until only the most powerful scopes can follow it. The time frame for such efforts spans mere weeks or months, not spanning years. Thus, each sighting matters immensely. Every cloudless evening holds value. Each captured light particle advances our grasp of this entity's true nature. Chapter 9. March 2026. The prospect of a Juno rendezvous. The study, co-written by Avi Loeb alongside Adam Hibbert and Adam Serra, delves into an idea that few, including many experts, would have deemed viable without seeing the meticulous computations laid out. Since 2016, the Juno probe has circled Jupiter, probing the colossal planet's gaseous layers, magnetic environment, and core makeup, all while gradually wearing down from radiation buildup and dwindling fuel supplies. The initial strategy involved plunging Juno into Jupiter's atmosphere come September 2025, deliberately ending the mission to prevent any risk of it later impacting Europa or another of the gas giant's moons with potential for life, thereby sparing them from earthly bacterial contamination. Yet Loeb and his team determined that rather than discarding Juno, NASA could steer it toward a meeting with 3I Atlas as the cosmic visitor swings by just 53.6 million kilometers from Jupiter on March 16, 2026. Central to this is delta V, the velocity adjustment needed to guide Juno from its present path onto a collision course. Their math indicates that a 675 kilometers per second boost on September 14, 2025, would align Juno for the encounter 6 months hence. Such a shift demands a hefty portion, almost the entirety, of the probe's leftover fuel, though it's conceivable if reserves prove adequate. The issue lies in uncertainty. Beyond the Juno operations crew at NASA, no one knows the precise amount of propellant remaining. Projections, drawn from the starting load, expenditures during the 2016 deep space corrections and Jupiter arrival, plus ongoing orbit adjustments over the last 9 years, hint at barely sufficient margins, with little room for error. The September 14th deadline passed sans any NASA declaration of endorsing the adjustment. On July 31st, Representative Anna Paulina Luna wrote to NASA officials, urging them to repurpose Juno for examining 3I Atlas, framing it as a rare chance to position human-built hardware near a sizable extrasolar body. Her message drew press coverage, sparked debates on TV networks, and stirred public advocacy for NASA to weigh the suggestion carefully. Still, bureaucratic resistance, caution toward risks, and rival demands, the typical drags on major choices in sprawling agencies, ensured that by the point of potential sign-off, the prime departure slot had elapsed. This doesn't fully rule it out. The research outlines options for propulsion later in mid to late September, revealing that although the needed delta V rises and the minimal distance to 3I Atlas deteriorates, a rendezvous stays within technical bounds at least into November. The best route incorporates a Jupiter Oberth assist, first lowering Juno's orbit, then firing engines at periapsis, where speeds peak and the craft sits deep in Jupiter's pull, maximizing the Oberth boost to enhance velocity gain per fuel unit used. The other option, a straightforward burn sans prior orbit tweak, consumes extra propellant but simplifies execution, with fewer elements prone to failure. Juno's array of tools turns out to be ideally suited for probing 3I Atlas's mysteries, despite not being built for this role. The near-infrared instrument can gauge heat radiation and bounce sunlight to limit estimates of surface temps and makeup. The magnetometer might detect fields signaling metal elements or induced currents, should the body produce or transport magnetic energy. The radiometer for microwaves can scan beneath the surface for heat profiles, seeking irregularities that point to inner warmth generation or stratified materials. The gravity investigation could assess 3I Atlas's mass, provided the pass-by range and speed allow for spotting gravitational influences. Variations in Juno's path could enable detailed observations. The particle detector for high-energy events would analyze the charged particles surrounding the target, shedding light on the solar wind's effects on the coma. The sensor for radio and plasma waves might detect electromagnetic signals, whether natural or engineered. The spectrograph and ultraviolet would chart emissions from gases in the atmosphere. The camera for visible wavelengths could capture images of the nucleus and its coma with clarity beyond what ground telescopes achieve. The proximity of the flyby plays a crucial role in the quality of information Juno gathers. The study examines various minimum approach distances, from tens of thousands of kilometers to just a few thousand, highlighting the balance between fuel needs and scientific gains. Nearer passes yield sharper details and stronger signals, though they demand greater propellant for the required adjustments. An optimal range seems to lie between 20,000 and 30,000 kilometers. This allows solid data from most instruments without exceeding feasible fuel limits for Juno's reserves. At such ranges, the visible camera might discern nucleus features as small as several hundred meters per pixel for a 5 km wide body, exposing surface details and shapes in remarkable precision. The infrared spectrometer would outline thermal differences on the surface, pinpointing zones of intense outgassing and potential hot areas signaling internal warmth. The magnetometer could pick up fields as faint as a few nanoteslas, thousands of times weaker than Earth's, yet significant enough for geophysical insights if detected. The radiometer using microwaves could scan dozens of meters beneath the surface, farther than visible or infrared methods reach, uncovering layers or structures hidden from surface scans. Gravity assessments stand out as especially valuable, offering a precise gauge of 3I Atlas's overall mass without relying on visual dimensions or albedo guesses. If the object's mass is indeed around 33 billion tons, as per Loeb's prior evaluation from absent non-gravitational effects, the gravity experiment ought to verify this through Juno's path curvature during the pass. A substantially higher or lower mass would necessitate updates to density calculations, structural theories, and material composition ideas for the nucleus. Low density might point to a loose aggregate of rubble. High density could mean compact rock or metal. Intermediate values align with the porous, icy makeup common in comets. The radio and plasma wave sensor might also catch broadcasts from 3I Atlas if any exist. Specifically, if artificial signals emerge in the 50 Hz to 40 MHz band where the device operates. This aligns with what Loeb highlighted in his discussion with Scott Bolton, Juno's lead investigator, at the MIT conference. Bolton noted plans to employ the WAVES instrument for radio signal hunts during 3I Atlas's Jupiter transit. It's uncertain from official comments whether this scan proceeds irrespective of an intercept or hinges on the tighter flyby from a targeted maneuver. Regardless, the tool functions and its band matches typical SETI frequencies. The storyline Loeb builds for this idea, scientific revival, is persuasive. Rather than discarding a nearly $1 billion asset that's still operational or staging a contrived crash into Jupiter for minimal planetary defense reasons when real contamination threats are tiny, prolong the mission by another year, another objective, another shot at groundbreaking research. Should Juno rendezvous with 3I Atlas and deliver conclusive data on its makeup, it would validate the mission's worth manifold. Even if the meeting uncovers no surprises, or if 3I Atlas proves merely an oversized comet with odd traits, the data would remain precious, groundbreaking, and a bargain relative to the mission's prior expenditures. The aspect of public involvement carries weight too. An encounter between a probe and an interstellar visitor, especially one as enigmatic and debated as 3I Atlas, would ignite widespread fascination far beyond standard Jupiter studies. The ensuing press, audience interaction, and spark for aspiring scientists and engineers all make such extensions worthwhile. When the scientific payoff from rigorous research remains unpredictable, NASA craves tangible victories, clear triumphs that highlight the worth of space ventures to funders and lawmakers who hold the purse strings. A rendezvous with 3I Atlas, particularly one uncovering unforeseen discoveries, could deliver precisely such a boost. Naturally, the downside involves the possibility of mishaps, a botched adjustment, errors in propulsion deployment or path computations, or glitches in the probe's hardware, leaving Juno incapable of fulfilling its core Jupiter investigation and forfeiting the 3I Atlas flyby altogether. Though improbable with flawless implementation, this scenario embodies a wager that NASA's established framework has long shied away from. It's preferable to wrap up the assured objectives, gather the essential Jupiter measurements central to the main goal, and execute the scheduled atmospheric entry, instead of jeopardizing everything for a tentative bonus objective, regardless of its intriguing potential. Jupiter's radiation field is ferocious, harsher than any other spot in the solar system, save maybe the Sun's immediate vicinity. Each loop Juno makes around the planet bombards its circuits with intense particles, steadily eroding functionality, corrupting data and storage, impairing photovoltaic arrays, and detection instruments. Come March 2026, the probe will have endured almost a decade in this harsh setting, amassing radiation exposure surpassing what most satellites face over full careers. Predicting if where has advanced to impair dependable functioning proves challenging. It hinges on individual components, build quality, protective measures, and sheer fortune. Certain parts could collapse suddenly, while others might endure well past rated limits. The true test lies in persisting with the flight, embracing the unknowns, and adapting to emerging breakdowns. Should NASA opt against rerouting Juno? If the September timeframe slips by unapproved, with no subsequent chance seized, the vessel will nonetheless perform that signal scan from its Jovian path as 3I Atlas sweeps past in March. The reach for pickup will be diminished, the acuity reduced, yet not absent. Should 3I Atlas emit a robust broadcast, a structured emission over mere background static, Juno could pick it up from distances spanning hundreds of millions of kilometers. It won't match the ideal scrutiny, the intimate pass yielding thorough profiling, but it beats oblivion. It surpasses ignoring the chance completely. The publication of the study, the buzz it stirred in outlets, the missive from Capitol Hill, all form part of Loeb's approach to harness societal momentum in swaying agency choices. As a federal entity, NASA heeds legislative scrutiny and societal sentiment more acutely than academic labs do. By airing the argument openly, underscoring the lost prospects of bypassing the Juno shift, and casting it as a shot at scholarly vindication against organizational shortfall, Loeb is wagering that outside forces will trump inherent caution and administrative drag. Success of this tactic is pending, though it's a method he's employed previously on varied matters, capitalizing on his visibility and press channels to steer discourse and advocate for results that raw expertise alone might overlook. Chapter 10. The 48-Hour Countdown. What unfolds at perihelion? On October 29, 2025, 3I Atlas reaches its nearest point to the Sun, 203 million kilometers out, about 1.36 astronomical units, situated between Mars's and Earth's paths, but on the Sun's opposite flank. From Earth's vantage, the setup feels dramatically staged. This pivotal instant stays veiled from straightforward viewing, masked by the Sun's brilliance, reachable solely via probes stationed across the system or via niche solar telescopes that could snag fleeting sights if aligned precisely and the body crosses their tight sight lines. The Sun unleashes gigawatts of energy onto 3I Atlas's exterior during these hours. Infrared, visible, and UV rays, soaked up by surface substances, transform into warmth, spurring evaporation, swelling from heat, and maybe even breakup if the stuff can't handle the heat disparities. Comets of natural origin do splinter at perihelion at times, not invariably, but frequently enough to qualify as a known event with defined mechanics. The warming proves inconsistent. The sunlit half scorches far beyond the dark portion. Heat-induced strains accumulate along the divide, and if the core is a loosely held rubble pile instead of a solid chunk, the uneven growth can rip it asunder. We've observed this unfold live with bodies like 73P/Schwarzmann-Watchman 3. This comet shattered into several segments during its 2006 appearance, with the pieces slowly drifting apart in the following weeks due to their minor velocity variations building up into noticeable gaps. The renowned comet Shoemaker-Levy 9 disintegrated due to Jupiter's gravitational pull in 1992, forming a chain of debris that slammed into the gas giant 2 years afterward in one of the most dazzling celestial spectacles on record. 3I Atlas possesses sufficient mass that its own gravity ought to keep it intact against typical disruptive influences. Yet sheer size doesn't ensure stability if the composition includes voids or internal cracks. The derived minimum width of 5 kilometers, based on the absence of non-gravitational forces, implies a substantial volume. Enough that, even assuming dense rock-like material, the speed needed to escape would only reach a handful of meters per second, akin to a steady stroll. Such feeble gravitational hold isn't robust. Factors like fast spinning, jets of released gas producing uneven push, or heat-induced swelling creating inner tension could easily surpass that weak pull, leading chunks to break free, rise from the exterior, and wander off into separate paths. Prior data on rotation indicated about 16 hours per full turn, resulting in surface speeds of roughly 1 meter per second for something 10 kilometers across. That's well under escape speed, so spin forces by themselves wouldn't hurl bits away. However, paired with gas emissions or heat-related strains, the turning could aid in fragmentation by unevenly stressing specific areas, focusing weak points in key spots instead of spreading the load uniformly throughout. Should 3i/Atlas split apart on its own, detection wouldn't happen right away. The resulting bits would look alike at first, each venting material, forming tiny envelopes of dust and gas, and following almost the same routes with tiny speed shifts. It would take days or weeks for the gaps to grow clear, as those starting velocity tweaks add up to separations of thousands or even tens of thousands of kilometers. How the light scatters among the pieces could reveal their size range. Did the split yield a handful of big chunks or a swarm of tiny ones? Was it a total explosion or a mild division into just 2 or 3 main parts? But if 3i/Atlas turns out to be artificial, if the idea of it being a parent vessel proves true, then closest solar approach marks the time for intentional moves over mere reactions to surroundings. At this range, sunlight delivers a fierce energy boost, ample to fuel major activities if equipped with gear to capture and employ it. Arrays of solar cells or heat-gathering devices might turn rays into power or harness focused warmth to spark reactions that draw fuel from nearby ices, energize signals, drives, or any onboard features. The schedule would be deliberate, aligning peak energy with prime chances for adjustment. The trajectory-altering plan that Loeb has explored in depth relies on firing engines near the sun, leveraging its gravity to magnify the push from any drive mechanism present. If 3i/Atlas aims to linger in our solar system, shifting from a hyperbolic flyby to a closed oval path, perihelion offers the ideal window. The needed speed adjustment, or delta V, hits its lowest here since the craft races at top velocity toward the sun. A modest slowdown of a few km/s, shedding just enough to fall under escape threshold, would convert a fleeting pass into an ongoing stay. Those far-reaching effects explain why Loeb's remarks on financial markets feel more like a grounded evaluation than exaggeration. Should 3i/Atlas execute maneuvers, clearly showing engineered control via directed thrust instead of aimless float, such proof would rank as humanity's biggest revelation ever. All other headlines and worries would fade against the truth that isolation ended, that an outsider entity entered our domain and opted to remain. Markets would tumble at once, not from outright danger, but from surging doubt. Old projections of tomorrow shatter. The arrival of far-advanced tech demands a full rethink of potentials and impending shifts. Pascal's bet carries extra weight in this case. Odds may sit low, perhaps 20%, 30%, or even slimmer, based on your starting views and emphasis on the oddities. Still, the fallout of erring, of pegging it as natural when it's really crafted, of neglecting to ready ourselves for potential encounters, engagements, or even mere sightings carries such enormous risks that even unlikely possibilities warrant close scrutiny. Dismissing a 1 in 10 risk of reshaping human civilization simply because the other 9 outcomes prove unremarkable would be short-sighted. The uneven stakes in potential results support proactive measures, warrant the resources and labor invested in vigilant surveillance, and demand we treat outlandish ideas with gravity despite their clash with everyday logic. The tale of the Trojan horse strikes a chord exactly for that reason. It's a cautionary yarn about flawed presumptions, perceiving only what one anticipates instead of the reality at hand, and dangers that masquerade as innocuous presence. 3i/Atlas resembles a comet in appearance, behaves largely like one, and shares traits with ordinary celestial bodies to the point where labeling it engineered feels like wild conjecture or needless panic. Yet Troy's guardians harbored parallel doubts about that wooden equine gift, offering comparable excuses for its likely innocence, enduring a communal pushback against excessive caution until it proved deadly, until the hidden Greek warriors spilled out, flung wide the gates, and the metropolis crumbled. Our edge lies in capabilities unavailable to ancient Troy, advanced devices and analytical methods that pierce superficial traits, uncovering faint irregularities signaling origins beyond mere natural phenomena. Orbital path data, density projections, elemental makeup proportions, and orbital alignments with planetary disks. All these factors impose limits enabling us to compute odds instead of relying on hunches. Those odds lack finality, offering no reassuring absolutes either direction, yet they furnish data, numerical evaluations that steer choices more reliably than gut feelings alone. From our vantage on Earth, the pivotal moments near closest solar approach elapse in quiet suspense. Absent immediate telemetry or streaming visuals from probes eyeing the drama, we're left with forecasts drawn from gravitational dynamics and simulations of comet habits. True insights will arrive in due course. As November unfolds with its exit from solar glare, the imaging efforts by JUICE commence, terrestrial scopes resume duty, piecing together the narrative of three atlases' actions or inactions during those concealed phases of peak solar energy and prime potential. The suspense gnaws at dedicated watchers, scientists, aficionados, reporters, all ticking down to November's end when sightlines clear and the post-perihelion condition reveals itself. Should it reappear in pieces, that bolsters a cosmic birthplace, implying solar heat overwhelmed its framework, causing it to shatter like typical icy debris under duress. Still, such splintering fails to dismiss engineered narratives entirely. A central vessel might intentionally shatter, dividing into modular parts that fan out to varied destinations, leveraging the split as cover for deploying scouts, rendering the sequence appear organic while enacting a calculated spread. Sorting these options hinges on meticulous exams of the debris traits, their dimensions, luminosities, paths, and signs of deliberate maneuvering. An unaltered emergence proves trickier to interpret. Many comets weather perihelion whole, particularly bigger specimens boasting sufficient pull and integrity to defy disintegration. Thus, a solid 3E atlas wouldn't confirm artificial roots, though it would sideline one common organic breakdown path, sharpening the field of options a bit, sustaining the tech theory's viability. True discernment emerges from path comparisons, pitting the inbound trajectory against the outbound one to check alignment within tolerances from vapor expulsion alone, or spotting variances hinting at extra propulsion from alternative means. Should it dispatch scouts, unveiling fresh diminutive entities absent earlier, directed purposefully at key solar locales, that strains natural explanations? Sure, one could posit accidental local shattering yielding fragments with apt speeds to graze worlds, but the odds of pure happenstance crafting such targeted precision dwindle sharply with more instances and accuracy. A lone unit veering vaguely Marsward might pass as fluke, but 5 units zeroing in on Mars, Earth, Venus, Jupiter, and Saturn, fine-tuned for timing and flyby paths? That's engineered. That's purposeful action no chaos of nature could plausibly forge. The notion of self-copying introduces yet another twist of intrigue to ponder. If those scouts harness nearby materials to build duplicates, functioning as von Neumann automata primed for rapid multiplication, their arrival here could represent merely the outset. This marks the start of a prolonged expansion that could span decades or even centuries. A modest starting group of probes kickstarts a vastly expanded armada, methodically surveying each intriguing celestial object. The pace of that growth hinges on replication speed, the duration required to collect resources and assemble fresh replicas. Yet, even cautious projections indicate that a limited founding cluster might expand to hundreds or thousands of devices over the span of a single human lifespan. The scenario sparks deep ethical and tactical dilemmas. Should we seek dialogue with self-governing probes? Might we endeavor to seize one for examination? Could we simply monitor them from afar without interference? Or would we implement safeguards against conceivable dangers, despite lacking signs of aggression? Resolutions to these issues partly rely on the probe's conduct, whether they maintain separation for quiet surveillance or venture near Earth's orbit, touch down on planetary surfaces, or engage in activities that encroach on human resources and concerns. Solutions also turn on global collaboration, specifically if countries can forge a cohesive approach or if they chase separate paths that clash or disrupt one another. Loeb's advocacy for UN guidelines and worldwide structures to handle off-world encounters stems directly from this worry. Today's handling remains improvised and instinctive, devoid of formal protocols for reacting if clear proof of extraterrestrial tech emerges within our solar system. Nations vary in their technological prowess, objectives, and governance styles, potentially yielding wildly divergent decisions on interaction, protection, or outreach. Absent unity, without shared guidelines and resolution mechanisms, the chances of errors in judgment or accidental intensification rise, fostering results no one desired, born from the clash of disparate players, each chasing their own agendas. The October 29th closest solar approach represents a pivotal juncture, an instant where uncertainties resolve into facts, conjecture yields to direct scrutiny, and 3 Atlas's essence emerges via its conduct, not merely its look. The coming weeks promise revelations surpassing the cumulative insights from prior months of monitoring, as actions amid intense circumstances expose traits concealed during calm phases. A comet nearing the sun unveils its authentic character, durable or delicate, compositionally standard or anomalous, inert or capable of dynamic responses undetectable by mere light reflection. Humanity faces a crossroads in its chronicle, possibly transformative should the unconventional hypotheses prove accurate. Alternatively, it could amount to yet another noteworthy yet conventional astronomical find, an exceptionally sizable interstellar comet exhibiting odd traits, ultimately attributable to natural mechanisms as data mounts. The vagueness feels uneasy yet true to the genuine unknowns, eschewing baseless assurance. Progress demands vigilant watching, amassing all feasible data, and scrutiny precise enough to separate theories based on their distinct forecasts for upcoming observations. 3 Atlas will disclose its identity via its perihelion maneuvers and subsequent path, whether it ejects fragments or probes or refrains, whether it emits radio signals or stays silent. Through countless nuanced indicators that together sketch a scene either reassuringly conventional or strikingly alien.